All right. Hello, ladies and gentlemen of Science 10. So we're taking a look at the Pedigree Charts worksheet. I've gone through and created a key. I'm just going to go through my solutions for this, and hopefully this will help you out if you are having some questions. So Pedigree Charts are important in many fields of science. One reason they're important is they help scientists understand the genetic patterns of diseases. And it's important to be able to interpret pedigree charts in order to learn the pattern of a disease or condition. Specifically, using a pedigree chart, you can tell if the disease's condition is autosomal, which means it's on the 22 non-sex linked traits, or a sex linked trait on the X chromosome, or dominant and recessive. So those are sort of the ideas that we're going to be taking a look at. So first of all, you need to become comfortable in making a pedigree chart. How can you tell if a couple is married? Well, easily you've got, remember, a circle represents a woman, and a square represents the male. And so a line between them, some of these things pop up. A line between them tells them that tells us that they're married. They've had, that they're married. How can you tell if a couple who is married has had children? Well, there is a line coming down from the horizontal line, and then you see the offspring, the children are there. So here we have two girls and a boy. Generally, this would be your first, and this would be your, it's supposed to be a three, would be your third child. So you'd be listed in chronological order. All right. So we have Mary is married to Greg, and they have two sons, Scott and Tyler, and a daughter, Karen. So here we have Mary, here we have Greg. This shows that they're married. This shows their offspring coming down. And so we've got Scott, Tyler, and Karen. As we go on, they add to this. So we've got Mary and Greg. They have Scott, Tyler, and Karen. Their son, Scott, married April and had a boy, Sutton, so we have the square for Sutton, and a girl, Kendall, is a circle. Their daughter, Karen, married Harry, so here's Harry, and they're married. And they have a son, Elik, and another son, Tariq, and this is how this would look. I'll move some things around. Okay. No, too far. All right, so here we have Julie is married to Jeff, and they have a daughter, Josephine. Josephine married Joseph and had sons Jason and Joe. They really like these alliterations. Joe married Julia and had Shannon, and paternal twins, boys, Mark and Alex. Mark married Allison and had Ray and Scarlett. Please label the pedigree. All right, so here we have Julie and Jeff. They're married. This is their daughter, Josephine, here, who married Joseph. Josephine and Joseph then had two children. We had Jason and Joe. And so we're interpreting the information, so Jason coming first and then Joe, that Jason would be their firstborn and Joe would be the secondborn. Joe married Julia, and they had Shannon, a girl, and they had paternal twins, Mark and Alex. So here we have two lines that are connected that show the two boys. And then we have Mark. So I had to draw this up there over the side, so this would normally be down below, but here we have Mark marrying Allison, and then they had Ray and Scarlett. Okay, so that was part of, here we go. So identify the following pedigree chart as autosomal, X-linked or sex-linked, recessive, dominant. Explain your answer. Is the following autosomal or sex-linked? Is it dominant or recessive? All right. So here we have a trait that neither the mother nor the father had. And they had boys that had the trait, and they had twin girls who did not have the trait. So I was saying this was an X-linked, a sex-linked recessive trait. Recessive, so that the mother would have been the carrier of the trait. So here's the mother, two X's, and there's the C representing the trait. The father does not have the C because he did not have the trait. If he did have the trait and it was recessive and sex-linked, then he would have that condition and his square would be filled in. So the X from the father, X from the mother. Here we have a girl that does not have the trait and a boy that does not have the trait. Here we have a girl that is a carrier for the trait and a boy that has a trait. So this is where we have two boys that have a trait. So they had 50-50 chance of the boys of getting the trait, and both boys had the trait. It's perfectly fine. Here, when we're dealing with percentages, it's over large numbers, not just over one or two. They could have had both boys who didn't have the trait. Then we have these two girls, and these two girls are either non-carriers or carriers, but the trait is not going to be expressed. All right, so let's go on. So here is the following autosomal or sex-linked dominant or recessive. And I actually went through and did some things. So here we have the woman. If it was a sex-linked trait and she has the trait, then I was thinking it was recessive to begin with, so she would have to have both the traits. The girls would all be carriers of the trait, and all boys would have the trait. So I saw here we have a girl without the trait, here we have a girl with the trait. And so was not going to be sex-linked. So here I have the idea that we have a carrier with the trait, heterozygous and homozygous recessive. And here we see the offspring. We have heterozygous and then homozygous recessive, 50-50 chance for those. And so if this was a dominant trait, so the capital A was the black trait, then we would expect to see for a large group, 50% having the trait and 50% not having the trait. In essence, that's what we have here. And so this is, scratching these things and saying they would all have to be carriers. And that made me sort of go back and rethink this. Dominant, otherwise everyone else must be heterozygous. So I was thinking first recessive and then went dominant. And that's, I think, probably a better. So heterozygous, homozygous recessive, heterozygous, and then it shows up heterozygous here and heterozygous here. So as the dominant trait is following through, and it doesn't depend on what the other parents are. So it has the trait, so it's going to show up here, just like 50-50 chance. Then carrying through, so here he has the trait, 50-50 chance. There's the trait, and then the trait's coming through. Anyway, so this seemed to be the best answer for this question. Now, this is the one, is the following autosomal or sex-linked and so on. So recessive, the parents did not have the trait. So here we don't show the trait, but then it's showing up in the boy and the girl. So that would mean autosomal, not sex-linked. And so otherwise we would be seeing it in both males. Because it's only the female that could be the carrier for that. So then coming through, you got mostly males, a couple of females. It just wasn't making any sense. And where it wasn't making sense was in these parents here, that it wasn't making sense that they did not have the trait. And so this is where I say there's something wrong with this question, and we're just going to ignore it. Okay, so here we have where you're creating pedigree charts and then determining whether dominant recessive. So Chad and Veronica got married and had Brittany, Kristen, and Harry. It was discovered that Harry had muscular dystrophy. Brittany married Larry and had Stephen and Stephanie. Stefan also had muscular dystrophy. Larry's brother also had muscular dystrophy, but neither of their parents had the disorder. So did not show up here, did not show up here, and then showed up here and showed up here. So the idea of this showing up in boys is what tells that it's sex-linked and that it's recessive. So Veronica can be a carrier of that. She has the two X's. Chad doesn't have it, so his X doesn't carry the gene, just one of Veronica's, and so that's why Harry gets it here. So sex-linked and recessive. I didn't show the Punnett square here, but that one is fairly straightforward. Here we have Lisa married Ashton and had 3 girls, Carrie, Mary, and Terry. It was discovered that Lisa had muscular dystrophy, so this is supposed to be colored in here. Come on. Okay, Lisa's covered in here. And then we had Terry married Perry. And they had 2 boys, Pike and Tyke, and it was discovered that Terry and Pike had muscular dystrophy. So this was autosomal because it was showing up in the females and in the males, and that's a dominant trait. So heterozygous, homozygous, and so when you do a heterozygous and homozygous, you can have 50-50 chance of offspring having that trait. So having 1 out of 3 is perfectly fine, and then having that trait show up again. When you're doing these so here you can see a heterozygous, homozygous, recessive trait, and we're getting 50-50 of the offspring. So doing a little Punnett square makes a lot of sense when you're going through these things just in terms of working out what we've got. So Deb married David. There's Deb, there's David. They had 3 children, Darren, Don, and Derek. David, Darren, and Derek discovered they have muscular dystrophy. Derek married Dee Dee and had 2 children, Denise and Destiny. Denise also had muscular dystrophy and married Dirk. They had 2 children, Dee and Devin. Dee has muscular dystrophy. So autosomal, because it's not following just the pattern of males particularly, and being a dominant trait, because again, 50-50 chance of that trait showing up. So here we had 2 out of 3 kids that had it. Here we had 1 out of 2 kids that had it. Here we had 1 out of 2 kids that had it. And so following it through. And that's it. Hopefully this made some sense. Short little video for that. Just wanted to try it out and see how you guys like that, whether it makes some sense for you. And what you can do is, so I'll have a bit of review on Monday and then a quiz sort of on Tuesday. All right, take care.